today I want to talk with you about optimizing explainability using feature selection with iterative ensemble interactions. If it sounds scary, it doesn't. Don't worry, we'll get into it in a second. So what's gonna happen today? So the agenda, it's going to happen. A quick introduction of expandable AI and feature selection, the optimizing feature ensemble for explainability, or the OIEI algorithm. This will be the main topic of today. I will try to convince you that feature selection will be really useful to have a more expandable AI, not only a more accurate one. This is my task for today. A few empirical results, because everybody looks like cool graphs, and additional thought and future work and questions if you have time. We won't. So the obvious slide of narcissism, because everybody until me was from Upsline and Riskified, etc. And because we have a small company, so we need to let you know who we are. So postdoctoral researchers in University College London. I'm the CTO of DataClue. We're doing life sciences algorithm outsource company. So if you have any problem with your genetics, for example, just let me know. One PhD in biomathematics, second almost PhD in computer science, and few years writing code. So to the main topic. A bit of definition just to make sure everybody is going to be on the same page. The presentation will be a bit academic. Excuse me for that. And so Expandable AI, or XAI, is focused to create an agent that are interpretable and transparent, fair, and faithful. So it sounds really like, I don't know, futuristic, so fair AI, or I don't know, faithful AI. So it's not it's not in the subject of this talk, but think about it. When we get an AI into medical or legal, we want to make sure that if we use AI to, I don't know, make decision in court, we want to be fair or faithful if we use it in a military-based operations. So a lot of things that we don't usually think about as AI, we starting to think about using a new fields and subjects. So let's define two stuff. First of all, interoperability. So you can read the slide. You bit kids at the moment already. So just give me 30 seconds about it. The interoperability is our ability to allocate the right explanation or the right process of logic to each action the agent does. Okay? Make sure that the keyword is the right logic. Maybe the answer or the action the agent does is wrong, but our ability to allocate the right explanation to why it does this wrong action is our ability to interpret the agent's system. More specific is explainability. The definition of explainability is our attempt or ability to post hoc fashion give a explanation to the agent's action. Make sure the keyword is a and not right. We don't necessarily need to give a right explanation, but we need to give some explanation. So this may sound like not big an issue, but believe me, it does, because the right explanation is really hard to find, but some explanation is a bit easier. So let's start with this one. Few motivations on, now when we agree that explainability is important, or what it is at least, let's agree that feature selection potentially improving both system performance and explainability. So maybe the first point, when the system performance is improved, you're more or less familiar with. You usually raise a head who use feature selection in the pipeline. So 99% of you. The 1% needs to start doing it. And explainability, it's not necessarily something that we talk about. In our work, when we work in with clinicians and we work in with politicians, we really find it hard to give them, we have really smart, I don't know, AI, or we have some kind of deep learning, and they said, cool, prove it works. And I said, yeah, I have really good metrics. Yeah, but why? And the answer, I don't know, is not a good answer. So explainability is something that we need to consider. And more than that, feature selection just remove features. But it sounds like really simple, but think about it. It actually gives you less features. It's like circular logic. But the less features make the relationship between the systems, dependent and independent variables, much clearer, because as a human, it's easier to concept less features. So motivation for our task. We have feature selections, we have explainability, and we have a lot of feature selection algorithm. So just feature selection algorithm. So you're probably familiar with chi-square, ANOVA, and etc., etc. So we have a lot of them, and picking the right one is by itself a really hard question, especially when you're talking on some kind of performance metric, accuracy, recall, F1, etc. It's even harder when you need to take into consideration other metrics like explainability. More than that, we actually get into something more sophisticated. Just a feature selection algorithm is usually not enough. You're actually combining a few feature selection algorithms. Just for example, you probably didn't think about it, but decision tree is actually a feature selection algorithm. You're making like the width, the max width to be a 4, and you have 10 features. You're actually asking the algorithm to reduce the features into like 4. So think about it. You have a few feature selection algorithms in the pipeline without even considering specifically. So we have a current feature selection and sample feature selection on improving the agent's accuracy and not explainability, which is fine, but not for this talk. So formally, problem definition. We want to find the feature selection ensemble that's optimized both performance and explainability. I have 30 seconds about that. What is feature selection ensemble? So basically, you have a list of set of feature selection algorithms, and you just want to have a feature selection algorithm which combining them in some way. It can be rule-based, it can be another machine learning model, it can be whatever you want. It's just a function that's getting a list of feature selection and operating as a feature selection by itself. Yeah, making it infinity large set of feature selection algorithms. Because, you know, just n size feature selection is not hard enough. So the idea, because we have only 50 minutes, just the main idea. You can see on the left, on your left, we have the feature selection algorithm. So it's marked by F1 to F5, basically F1 to Fn, have a set of feature selection algorithms. And basically what you're trying to find is the point that's optimizing your accuracy and or explainability, or both, why not? But this is really hard, and the number of combinations can be huge. So we're doing something a bit different. In our approach, we've taken the problem from the feature selection algorithm space into a new space, T1, T2, T3. So T1 is the size of the feature selection set, not the algorithm, the set itself, so the outcome of the algorithms. T2 is a parameter saying the amount of interaction, the pairwise interaction between any two feature selection algorithms in my data. So let's say F1 and F2. I need to have some kind of maximum interaction between them, which is defined by T2, running from 0 to 1. When 1 is we have full interaction between them, and 0 is we don't allow any interaction. So, by the way, 0 is really bad. Usually don't work. T3 is the amount of the kind of interaction. So T3 is interception, while T3 equals 0 is the full union, and T3 equals 1 is full intersection. And every value in between is just a linear combination between these two extreme cases. So we define T1, T2, T3. And just notice that the T1, T2, T3 actually doesn't consider anything or don't have any assumption on the feature selection algorithm space. It can get any feature selection set of a feature selection algorithm set, and actually performing an optimization on the interactions rather on the objects themselves. So we're actually able to solve the problem on this space. Once solving the problem in this space, we just convert it back and get an answer of in the original space when we want it. So it looks like that. You don't really need to read everything, just if you want, and it's recorded, so you can review it later. But the main idea, we have an optimization process. So you can see it in line 3 while OC, it's while an optimization condition is happening. What is not finished, as you can see on the right, we select T1, T2, T3, performing the feature selection algorithms, all n of them, get a ranked feature set 1 to n, the red ones. We get an aggregated method, which is the outcome of T2, and the outcome of T3 is the feature set in green there. Okay, if that point is good enough, or not good enough, actually, we doing this again in iterative way, trying to optimize the optimization process. While it's good enough, we just finish and get a feature selection set, which is really good for us. As I said, an academic presentation. So the complexity lovers, memory is maximum between n and the number of feature selection. M is the number of interaction between them. So it's NM maximum FSAM stands for the maximum memory consumption of the highest maximum memory consumption of the feature selections algorithm. Yeah, just like make sure that we don't forget the feature selections, the computing time and memory consumption of the feature selection themselves. In a similar way, the complexity is as follows. The long story short, as you can see, it's a polynomial to the size of the set, which make it really useful in production. And this is the algorithm. So let me convince you, because it sounds really good in theory, but I need to convince you it's actually working. We took 9 different data sets. So you can see most of them should be familiar for most of you, because it's really like canonical data sets. But the idea is the domain is really different, as you can see. Have ECG records, voice recognition, mass hyperconnectivity, so we have a lot of domains. And we have a few data sets with the course of dimensionality. In course of dimensionality, I mean the number of features is relatively much more than the number of samples, which consider a hard problem to solve, especially in feature selection settings. More than that, let's define expandability, because now we have an idea, let's make it formal. So the definition above is from paper from Rodin in 2019 from a Nature paper, and the definition below is what we're using, actually. So just to call it by its name, it's just the size of the feature selection set. You can argue this is not the best definition, which you're probably right, but it's good enough for us, so let's use it. More than that, just optimizing the expandability is actually really easy, because just take one feature and that's it, you win. So not so much. Let's define a performance, the total performance of the algorithm, or the case we want to solve. We using a harmonic mean between the accuracy and the expandability. Okay, why a harmonic mean and not like regular mean? Because the harmonic mean considered to be harder, and we're trying to get the hardest task, just to showcase that we can. And the following results are that. So using this expandability and taking the 9 datasets, we can show that in T1, this is the heat map between T1 and T2, as you can see. By the way, T3 is actually located here because each value in the heat map is an average over T3 between 0 and 1. Okay, so it's just because it's really hard to show like a 3D heat map. So this way. And the function above is a polynomial interpretation of the heat map, which you can see it's basically good, 8, 9. And the interesting stuff is you can see the coefficients of the linear T1 and T2 is relatively small to the second order T2, saying that the second order interaction between the feature selection algorithms is much more important to the outcome than the linear of these parameters themselves. So this is actually really interesting. When we break down the data into smaller chunks, so smaller chunks, so we can see the algorithm if we actually win in 5 of 9 times, which is really good. If it won 9 out of 9, this is the fabricated data. So this case, that's real. So actually baseline is won 2 times, which is strange, but data. This is an aggregated view. As you can see, we win in the competition. So until now, expandability is great, but what about stability and other features that we can use? So does our algorithm is able to improve stability? So the answer is, well, yes. And let's define a stability. I'm sure everybody is able to read this by themselves, because I won't. I can't. So another heat map, again, just notice that the linear coefficient is much smaller than the T2 square coefficient, which saying that we actually get a repeated results, making us believe this is actually really interesting. Again, 6 of 9, and again, it actually sounds really cool. So just to conclude everything, the main contribution is as follows. So OIEI that you can use, I will show you the link in a second, is able to consider explainability as a problem, not only the accuracy on other performance metrics that you use to work with, and actually improve both of them. So while you have a trade-off between explainability and the performance, we can show you can actually push the trade-off a bit further using this approach. More than that, OIEI is in a parameter free. You may ask yourself, because if I presented you T1, T2, T3, how can I say this is a parameter free? So the answer is actually really easy. We find T1, T2, T3 using an optimization process. Namely, we don't actually provide it into the algorithm, it finds it by itself. It's just a way to represent the problem. So it's a parameter free, which is really good because usually the other feature selection algorithms using some kind of parameterization in order to be really useful in the feature selection process. So it's parameter free, which is great. And just to convince you even further, it actually has been used in 2 projects and give us good results. So we know it's fine. Just a quick thank you for Professor Avi Rosenfeld and Dr. Svetlana Bonamovich for the help in this research, the entire research. And I will study, we are really interested and really looking for any kind of both research and business collaboration. The old version of the algorithm can be found on this link. So take a photo if you want, and that's it. Thank you very much for your attention.